Hi, how you doing? It's Bob Sorensen, but now I put on my chief analyst for quantum computing hat just to give you a basic overview of how quantum computing right now is finding its place in the overall advanced computing sector. As we all know, I think the promise of quantum computing is certainly substantial. They have the potential to exceed the performance of conventional computers for problems of real importance in areas like physical simulation that include material science, chemistry, pharmaceuticals, and even the oil and gas sector. Other interesting application spaces right now that we're tracking with great interest, opportunities in machine learning and optimization, which has wide applicability in a number of sectors and is really generating a lot of interest in what quantum computing can bring to the advanced computing performance table, if you will. An interesting thing is that the application list, the use case list for these devices just seems to grow longer and longer every day. Now, if you listen to what the quantum computing experts will tell you, the goal really is to demonstrate at some point quantum supremacy. This idea of using a programmable quantum device to solve a problem that no classical computing counterpart can solve in any feasible amount of time. And by feasible amount of time, some of the things that say were brought to the fore by Shor's algorithm, factoring a large number into its two prime integers, something that may take a quantum computing hours, if maybe a day or so, is something that if you tried to implement that same function on a classical computer, it could exceed the time of the known universe to reach the same conclusion. That's the vision of quantum supremacy. That's a long way off. That's something that the sector shoots for. But really, what we're in now is a stage where there's lots of promise and potential and uses of quantum computing long before we reach that eventual quantum supremacy capability. Indeed, many people aren't terribly concerned about quantum supremacy as long as quantum computing can deliver performance gains that are better than what they could achieve on their classical counterparts. Interesting point I just want to really drive home here is that there are very many different ways in development right now to actually implement the quantum phenomena required to basically generate a quantum computing system. And some of these modalities, superconducting qubits, photonics, trapped ions, spin quantum dots, are all under research. And this chart on the right here, the typical apology for the blinding eye chart here, just shows the breadth of research that's going on in a number of different organizations. The key takeaway from this is that the quantum computing sector has not coalesced yet. It hasn't settled into a particular choice. It's not as if we're saying, okay, in the classical world right now, silicon-based CMOS is the sine qua non of semiconductor format. In the quantum world, there are still very many different modalities, each offer their own unique strengths and weaknesses. Ultimately, there may not be a clear winner among these modalities. Certain modalities may offer performance enhancements for certain kinds of applications or algorithms, and ultimately, the winner, the ones that actually reach the end goal of becoming the standard in quantum computing may not have even been invented yet. I almost liken it to saying the times when we were looking at classical IT systems based on tube technology, long before transistors, long before integrated circuits came along. So there's still lots of uncertainty here, but also lots of opportunity for a lot of different folks to explore different physics. This just leads really to some sense of the substantial challenges ahead that we see. The technical issues are irksome. Quantum technology is uncertain. It's a research activity at this point. The performance gains, again, quantum supremacy is one thing, but to really generate demonstratable capabilities above classical counterparts is still a work in progress. The time frames are something that you just can't predict on it. This is not happening on a standard development schedule. And there are some looming workforce issues. Are there enough people out there that we can either bring out of school or retrain from the advanced computing community to really deal with quantum computing if that market should grow at the way we think it is? Ultimately, this complicates treating quantum as a stable market. And so making a business case right now is tough, but it needs to be done in order to assure that funding and interest and research continue in order to help this technology reach its greatest potential. I just want to give a sense here about the sense of quantum computing as an international phenomena. If you look here on the chart on the left, these are research publications for select nations over the last 5 years that are involved in R&D, publications, and well-respected technical journals. If I did the run about 3 weeks ago, came up with about 17,000 documents. It's pretty clear that the China and the United States and Germany published an awful lot of papers, but that tail is long and broad and diverse, and it goes on and on. I just ran out of space here. This is a global research phenomena. The chart on the right really highlights that, I think, because what we see here is this is quantum computing publications by count, by affiliation, kind of drilling down that chart on the left. And if you just run your eye over that, you see there's participation in China, in France, in the United States, the Netherlands, Canada, the UK, and Singapore. This, as I said, this work is going on around the world with great enthusiasm. And so the idea that this is a technology that may be held by one nation or ultimately dominated by one nation, it's way too early to pick winners and losers. And any particular nation has a significant chance of actually realizing some performance gains, some capability, and some world-class activities in these particular areas. And all I do is I point out that this is really driven by government programs at this point. This is simply a smattering of the government programs that are helping to drive quantum computing right now. And it seems like almost every day we see more and more developments. As I said, this is a risky business process at this point in time. And so this kind of government support, its early stage of the technology adoption as it finds its financial footing, these kinds of programs are critical to continued success. I just want to quickly, point out that while the government's involved, there is a wide range of hardware and software suppliers in the ecosystem out there. Legacy players like Fujitsu and IBM and Atos that bring their classical IT skill set. Number of new entrants around the world. Pure play companies like IonQ and Rigetti, and then even some non-traditional players like cloud service providers, Alibaba, AWS, and that like. I cannot, I would be remiss if I didn't say that the European commercial presence right now is substantial. This chart is hopelessly out of date because the only way it could be on time is if it was real time. There is a wonderful breadth of companies throughout the entire quantum computing food chain, their entire ecosystem, developing fascinating new technologies, just proving once again that this is not a legacy system, that a country or organizations that can literally rise out of the startup environment to really make a splash in terms of quantum computing. Opportunities abound in this sector. I just point out these numbers of quantum computing suppliers from the software perspective here, not to amaze you with the ability for me to cram a number of companies into a single graphic, but to point out across the top that right now the quantum computing ecosystem has coalesced to the point where if you're writing software applications, you don't need to pick and choose a particular winner when it comes to a hardware vendor or even a quantum modality. So take example, 1QBit, the company on the top left. Their software is amenable and can be run on a wide range of quantum hardware suppliers, including companies like D-Wave or Honeywell or IBM or Rigetti, which all have somewhat different kinds of architectural characteristics, and yet the software works. And what that means is there's a lot of opportunity for software companies to bring innovation to the sector without having to tie themselves to a particular modality or a particular hardware vendor. And I find that to be a very satisfying thing. Well, we recently came up with some forecasts on quantum computing, and I'll go through this quickly. We did a lot of background work, interviewed about 250 different quantum computing companies around the world to get a sense of what's going on. We came up with some numbers. The market's worth about $320 million in 2020. We're looking at about a 27% CAGR growth rate. On-prem and cloud access quantum computing hardware will be about half the market. The holy trinity, if you will, of applications will be evenly divided between optimization, physical simulation, and machine learning, the applications I mentioned earlier, and really user access to cloud, user access to QC will be primarily through the cloud at this point, really at about 3 times the rate of on-prem options for at least the next few years. Last thing I want to point out before I run out of time here is that story I told in the beginning about quantum supremacy. Well, we went out and asked about 115 different users of quantum computing, or those who were thinking about using quantum computing, and asked them what their requirements are for justification of using quantum computing. And really what you'll see there right in the center on the right there is that bullet that said 42% of the respondents said as long as they get 50x performance improvement over their existing workloads on classical computers, they would be more than willing to basically adopt quantum computing into their overall computational workload. And to me, what that says is this quest for quantum supremacy or very, very impressive performance speedups, that's something that maybe the supplier community seems to be more attached to, when the potential user base just says, give us 50x, or even 20% said, just give us 10x, and we'd be very happy. And what that number means to me is, say 50x, that really just says they're looking for about a 4 to 5 year bump over what they would see in a classical computing performance gain. And to me, that doesn't signify very esoteric requirements. It just says they're looking for some kind of performance advantage when it comes to using quantum to actually just do their work. So I find this to be a very interesting and somewhat satisfying expectation level for what the users are really thinking. It's modest, it's realistic, and it doesn't really stress the technology all too much. This is some things we can talk about if you want to continue the conversation at some other point, how this all comes out near term. The one takeaway here, the bullet right in the center, just want to stress quantum computing is not a replacement for classical, but a companion. If we could turn back the clock, I would like to call this quantum acceleration, much the same way that GPUs provide some very impressive performance for a specific range of applications in the advanced computing world. Quantum computing will fill much that same role once they reach the level of sophistication and standardization where we can think of a quantum accelerator as a black box resource in your overall advanced computing environment. Well, that's enough for this. If you have any additional questions, want to get a hold of this deck, or just talk a little bit more, here's my email address. But I want to thank you for your attention today, and I hope you enjoy the rest of the presentations.